us?
Barely. This is my microphone. That's why I have this obscure microphone up at the front here. But it's not pointing directly to you guys. Okay, so here it is. And all right, so this is like my new projector. It's like this little one here. Okay, so few things today. We're supposed, like, you would think that we're going to cover we covered 5.6, 6.1. So far, only those two sections. So I think those were the biggest. We did not cover 6.2 and 6.3. They're actually a lot like 6.1. They're all sort of related. So next week, I'll touch on it a little bit on 6.2 and 6.3. But today, we're going to learn about the main content from section 6.4 and 6.5. Okay? So it seems like I'm going to jump around a little bit, but I think it's kind of organized a little bit better if we do it this way. Okay? So the handouts too, by the way, that I handed out to you guys. Let me get to that really quick. Let me show. Did everybody get one? Did you guys all get one? Yeah. So there should be 3 handouts, and they'll all be found online on the website right now. I just posted them. There will be keys to these as well. So these are So sorry, these are just for the people that aren't here. So these are the 3 that should have been given out. And then if you go to my website, let's see. 2 of these are worksheets, by the way. And under month 5, I added, like, last time I added, like, there's week 1 stuff, week 1 and 2. Week 3 now has these following handouts. And then these I'll add in, like, maybe over the weekend, just the links to the keys. Okay. So without further ado, let's actually start with like a quick warm up, right? So if I were to tell you that let's say that I took the derivative of a function, okay? If I took the derivative of a function, that's actually really hard to see. Let me grab another pen, okay? If I took the derivative of a function, okay, with respect to x, I could write it as this, or I could just write df over dx, right? Let's say the derivative was 3x squared. Could you find f of x? Let's go backwards. So Omar, go ahead and grab one of each of those. We just started class, okay? We're not going to do 6.2 or 6.3 today. 6.4 and 5 are, I think, the big ones to hit. So that's what we're going to try to go over today, okay? 6.4 and 5, if you're familiar, right? So here's my question. So I think Aaron's coming in too. So try to figure that out right now. Aaron, pick up one of each of those handouts. I'm recording right now, so that's why I'm kind of talking kind of funny. They're online too, and keys are about to go up as well tonight or over the weekend. And answer me this question. I just asked this question over here. Today we're just covering 6.4 and 5, okay? So we're going to jump around the sections. We skipped 2 and 3. We're going to come back to them like next week, like during the actual class, all right? So here's the question I posed to you. If your derivative of your function is equal to 3x squared, what was the original function? Can you go backwards, okay? What was this equation? And then if we took the derivative, we got 3x squared. Can anybody solve for that? What would be the original function? Yes, Skylar, what do you think it would be?
X to the 3rd power.
Okay, so let's just say hypothetically if f of x, so don't write this part down. F of x was x cubed, and we took the derivative of that, then what would we have to do? What are the steps to finding this derivative? Like what would we have to do with the exponent there?
So we would have to put the 3 times the x by 3 and then subtract 3 by 1 and make that the power, right?
There we are. So see how kind of we went backwards? So here, going forwards, we take the derivative, we did the power rule, right? Where we took down the coefficient here, and then we subtracted 1 from it. But going backwards, it's like you have to stick back that 3 up back in the corner, and then there's no coefficient anymore. So here, your answer is indeed x cubed, okay? Sort of like you're taking the antiderivative of the function. How about this? What if the df of dx, what if that was negative sine x? What would be the original function? Now, I think I see someone that knows. Please look at one of the handouts I just gave to you here. Look on the back. Oh, hey, Christina. Thank you for joining us. Go ahead and pick up one of those. We're going to go over the last two sections. We're going to look over the last two sections of the book or for this month, okay? So go ahead and have a seat. I just started notes, Christina, so here's my note. If I just took the derivative, if the derivative of a function was negative sine x, what was the original function? And then how about another one? df of dx. What if I said the derivative of the function was also 500? What would be the original function?
Wait, 500x. Yeah.
Huh?
500x, and that would be cosine.
Ooh, actually, too, 500x.
Plus
Aaron
c.
said. Okay, that sounds weird. Okay, and then this would be what?
Cosine.
Because if we took the derivative of cosine x, what would the derivative be? Negative sine x. Plus c. Yes?
Why would it be plus c?
Okay, why would it be
Because c
plus?
could be like 5, and then in that case it'd be plus 0.
Dang, that was really good, actually. Did you do these sections yet or no?
No, I haven't even started on the work.
So was my first answer incorrect in any way? Would I get any points marked off? Would you think if you were the?
I wouldn't, because I'm a nice teacher.
I see. Well, me being
that
a
is correct, but it doesn't show all of the equations.
So it's not-
all of the possible.
so by a mean teacher standard, this is not a fully correct answer. Okay, so it should have been plus c. Oh, that's this being my personal laptop, you're gonna get personal messages about surfing. Okay. All right. So that's the warm up. We're gonna need this today. Okay, we're going to need this skill today to kind of explain some of the concepts that we're going to learn today. So again, 6.2, 6.3, those sections are a lot related to 6.1. So I'm not really going to go over those today. I'm going to go over what's called integrals and the trapezoidal rule, right? So this is something that we'll need to talk about today. And how about we keep going with this though? Okay. Maybe you didn't see this, but on the back of this handout over here, these are a list of derivatives, derivative cheat sheets. Okay, so in this one, it's kind of hard to see, but it says the f of x is equal to k something r. Does anybody know what that means right here? K r what?
Is the r real number?
Yeah, any real numbers with no variables. Just like what's a real number? Someone just 2 is a real number. How about -1? Is that a real number?
Yeah.
How about a half? Is that a real number?
Yes.
How about I, the imaginary number?
No.
No.
Because that's literally imaginary, right? The derivative of any real number is 0, right? Doesn't that make sense?
Yeah.
If you took the derivative of a constant, that'd be 0. So the way you read this is if you have fx equals x, then the derivative would equal 1, right? And so forth. Okay, if fx was equal cosine, the derivative is equal to negative sine. So this is how you read the derivative cheat sheet. That being said, can you solve this worksheet? Okay, so yeah, Deja,
What does the on the other sheet? What does the e mean?
E, which one?
No, not the not the like e that's 2.8 whatever.
Uh-huh.
The KER, that one. What does that
Oh,
mean?
yeah.
cheat
He just did that. The
Oh, this one here?
if it's
Yeah,
any
what's
real
that?
number.
It's
So
like
it's just like equal.
I thought the cursive R meant real number. What does the e mean?
oh, that just means this could be I think it's inclusive or it could be you could replace k with any real number. That's what that. It's not an e, but it's just like a notation in math saying we're talking about any number within this set. Okay, so it goes a little bit into upper level math about talking about sets of numbers. So this number could be within this set of real numbers. Within the set of real numbers is every number you can think of except I. Okay. Okay. So it's just
I've never seen that funny looking symbol.
it's okay, and we kind of glance over these kind of things when you see them in like high school math, okay? But when you get to college, then you start using it and really understanding what it means, right?
Okay.
So that just means within the set of real numbers, okay? Good question. Very good question. Okay, so let's go ahead and try this for like about 5 or 10 minutes. Let's do this for about 10 minutes. Let's see how far you get, and then I'll put up the key for this, okay? So let's do some matching here. So here's the function, and here are the sides of the antiderivatives. Can you solve for the antiderivatives, okay? Don't forget about the chain rule. There's a chain rule to follow as well. Does anybody want the air conditioner on?
No, thank you.
Okay.
Yeah.
I'm gonna charge. Anybody get A's or not A, number 1 so far?
Yes.
Okay, what did you?
That was the warm up.
Yeah, that was the warm up. So what letter should that be? J. I like how J. And guys, if you guys don't know, ask each other around. Skylar, take advantage now because you're now with people, so you don't have to experience this experience alone anymore, okay?
Wouldn't that be negative?
Anybody get number 2?
To get this.
Number, okay.
That was the warm up too.
So if you take the x over 2 is just a pi chain. Takes one to the derivative. So derivative e to the x over 2 is going to be 1/2 times e to the x over 2. So if you put in a 2, it would just cancel. Or yeah, e to the x just
Okay.
the x.
How about number 3?
For some reason I thought you'd have to like subtract 1.
3 is just negative cosine.
But I don't know what that is. What is it? Where is negative cosine? Okay, thank you very much. That's true. Okay.
Or
4 is really tricky. What's the derivative or the antiderivative for e to the x? E to the x. Very, very good. That's it. Uh-oh, number 5. Yikos. Yike-os.
5.
Uh-huh.
I got x to the wait, what was that?
3x
Yeah,
to
3x.
the 4.
How'd you guys know that it was 3x to the 4th?
Because it
I
has
took
a
a while
12
to
in front of
guess.
it. So like, you know
Why did I
that
put
Oh.
the power would be 4
Uh-huh.
because it goes down to 3. So then you have to find out what you have to multiply the 4 by to get 12.
Okay, so notice that if you took the derivative of x to the 4th, right, it'd be 4x to the 3rd now, right? But remember, there's already a 3 in the front. So with that 3 being in the front, you have to multiply what you just carried down, 3 times 4. And what would that give me?
That's amazing.
That is amazing, isn't it? Yes. You have to get really creative with some of these guys over here. So 12x to the 3rd, you would put O. Okay. This next one is a little tricky. So if you have a hard time doing this one, you could also rewrite 1 over x squared as x to the negative 2. Okay.
I think it's
I got negative x negative 1.
So negative x negative 1, which is, where would that be?
I don't know.
You don't know?
I
Oh.
don't know. I haven't looked yet. Oh, it's negative 1 over x. So
Yeah.
n.
So
It's
look.
on the derivative cheat sheet, like, except without the.
Is it?
Doo, doo,
no,
doo.
it's not.
Well, except
It
with the
sort of
negative.
is.
So can't you just do negative?
Does anybody understand why? Just as a reminder, back to those previous chapters a long time ago, why 1 over x, the derivative would be negative 1 over x? Why would that be? I do not know. I don't know. If I had to rewrite this, you don't have to do this on your cheat sheet, but as a reminder to myself, you could rewrite this as x to the what power?
-1.
Uh-huh. So if you did the power rule to find the derivative of that, what would you have to do to this number down here or up here?
Be -1 x to the negative
Subtracted by 1.
-2. Yeah.
That's what you got. Uh-huh. And if we had that, it'd be negative x to the negative 2nd power. Can I rewrite that again?
1 -1 over x squared.
Oh, and that's what we have over here, don't we? Only, trick, what are we missing here to here? We don't have a negative sign there. So you gotta get really creative and then say that not only is it the derivative of this guy, or I'm sorry, this the derivative of this guy of 1 over x, but it's -1 over x. So watch, if you rewrite this, it'd be negative x to the negative 1st power, right? If you took the derivative, it would be -1 times that negative sign, which is another -1, times x to the negative second power, and then you get x to the negative second power, okay? So this should be n. That should be n. Confusing?
A little bit.
Definitely this is something that if you explain more and more, it might not help, but if you practice it enough, or if I say it out and then you just kind of sit on it, let it soak in your brain for a second, and you're like, I still don't get it, and then you try it, you're like, oh, what he said kind of makes sense now. Okay? It's one of those types of learning. Okay, actually, college is a lot like that. Pretty like you have more of that type of learning where you're like, what? Oh, okay, I think I get it. That type of learning. Right? These AP classes really are a good taste of like what college kind of feels like. And you can, not to discourage you at all, too. I think your brain will be ready for it by then, too.
Is there an easier way to do all of this stuff? Because I'm just thinking, what if we have a super long, crazy function? There has to be some kind of little trick to find the.
Your trick is just to know the derivatives fairly well. Yeah.
Okay.
Not inside out, but maybe fairly well would get you by. Okay. If it helps, you can also just take you won't always have this option, but you could also take the derivatives of these antiderivatives and match them here. But it's better to kind of try to make this try to think backwards for this one, for these ones, okay?
Take the derivative of the antiderivative?
Yeah, but you won't always have the option to do that, you know? It would just straight up tell you what should be the antiderivative, you know? But in this worksheet, you can kind of work. You can work backwards in that way. You can take
more complicated ones. You won't be able to do that.
Well, in the future, they're just going to ask you, can you find the antiderivative?
Oh, I get
Do you see what
you're
I'm saying? Like,
yeah.
can you find the antiderivative for this?
Okay.
I don't know. Anybody find number 7?
I got 2e to the x over 2.
What is it? 2e to the
So I think
x.
that's
C.
Oh, that's C. Can you show me up there why on the board? So sorry, folks. On
Well, I kind of played around with it. That
Uh-huh.
one isn't that easy just to do kind of in your head. So, basically, I forgot which one I'm doing. I'm sorry.
oh, you're doing the antiderivative for this, and
X over 2.
you're saying it's C.
X over 2.
Yeah, e to the x over 2. So if you just took the derivative of this, for instance,
Uh-huh.
You would get e to the x over 2 times 1/2. So if you just added 2 to the beginning, because the constant stays, and then it'll stay here, and they'll cancel. You'll just get e to the x over 2.
All right, so let's see what you got. Can you sorry, because your beautiful pale hair. Pale, right? Is that Espanol for hair? No? Okay, your hair and your beautiful head is a little bit in the way. For me, from my perspective. So I just need to see what you're doing right now. Okay, so I see. So you're saying if you had did you guys all get that sort of here?
So I started by just
No,
straight
I put
anti-differentiating to go straight to the e to the x over 2.
So
Just assume that, for
Okay.
instance, the antiderivative is e to the x over 2.
Okay, so so you just did it like this, like
Just start like that, yeah.
okay,
And
you
then
just, and then you take the derivative.
derivative of that to get back to check my answer, you get 1/2 is the coefficient that's remaining.
Okay.
So if you just added 2, then
Oh, I see what you're saying. So you're saying the antiderivative, or let's see, the derivative for this would be e to the x squared, right? But also the chain rule. Don't forget the chain rule. If you took, so let's just kind of work backwards, right? So what we have up there on number 7, right, is e to the x over 2. So what Aaron says is just kind of look at the basis for it, right? And then kind of like take the derivative of that. Let's just see just take the derivative of that, right? And then the derivative of e to anything is what?
usually e to the same thing. So
It's e to the same thing. But when you're taking the derivative, don't forget, because the top part does have an x in there, you have to take the derivative of that part as well. So what is the derivative of x over 2? Anybody know what the derivative of x over 2 is?
It is 1/2, right?
It is 1/2. It's sort of like saying what's the derivative of 1/2 x? That's just 1/2, like Aaron said. So if you look at it, number 7 though isn't 1/2 e to the x over 2. It's not. That's not what we see, is it? So look at number 2 or number 7. Look at number 7. It's not exactly 1/2. So what would have to be there for the 1/2 to cancel out in the first place?
2.
The 2. So it would have to be 2e to the x.
So that's why it's C.
So that's why C, because if we took the derivative of this, right? If we took the derivative of this, the 2 would stay there, and then we would have times e to the x over 2, 1/2, and then these would cancel out, leaving us with number 7. Okay? A lot of talking and a lot of craziness there, right? I think Aaron's explanation is a little bit more eloquent and short. Okay.
I honestly no. It just makes sense to me.
It just makes sense to you, right? I mean, that's kind of what this exercise is making sense of all this stuff. It's not easy. It's not particularly easy at all. I'm curious, is anyone on number 8 or 9 already?
Yeah.
How about number 10?
Yeah.
Wow. 11?
I
I
couldn't
got
figure
stuff
that
on
out.
it, yeah.
Oh, this one here. Okay.
I'm just gonna do all the other ones and do process eliminate.
You can do that too. Number 11 is a really good exercise. That's a really tough one. Okay.
13. Yeah. It's just,
So-
I distributed it out. So you have
It's
x
probably
squared
A, right?
plus 2x. Yeah.
So 14 and 13 look like they're going to be really tough.
Number 7.
Yeah? Oh, sorry. You go ahead. Go ahead. Yeah.
If you divide e to the x 2, you get that. Do you remember the derivative for e raised to something? It's just itself and then the derivative of what it's being raised to. You'd have to remember that.
Okay.
That's just so it's itself times the derivative of its exponent, and this is just the quotient rule.
Here's another tip too. Maybe I can make this add. You guys see how it's this one, number 8 is x to the 3rd over 3. Pay attention to just the guy with the variable. So it's just pay attention to x over 3. Okay. Can you tell me what the antiderivative with that for that one would be? So just look at x over 3. What would be the antiderivative for x over 3?
X to the 4th.
It'd be x to the 4th, but remember, if just thinking backwards, if we took the derivative of this, then this should have came down, right?
Mhm.
So why is this not 4? Why is there no 4 there, but instead we have 1/3, if you think about it? So that's the question you have to ask. It's like, okay, you see how if you took the derivative of just x to the 3rd, it should have been x to the 4th, right? In fact, not just x to the 4th,
2 left, yeah.
Should I just have a plus 1?
but why is it 1/4 x to the 4th? So what I'm trying to say is this here. You see how if I just focus on x to the 3rd and I took the antiderivative,
I thought it would have to
not only is it x to the 4th, but it's 1/4 x to the 4th. Because I know if I took the derivative of this, right,
So that way,
we would drag down the 4 and that would cancel out. Does that make sense?
so
But
you can just distribute it.
not only that, we have that 1/3 added there as well. So that makes it really confusing. So let's see. You would have to ask, what do I have to multiply to 4 to get to 1/3? So I don't know if I'm making it any simpler. Okay, so this is getting a little bit tougher. Yeah.
Could you explain 11 and
Sure.
'cause that's
So number 11, let's say it's actually going to be sine to the 3 or sine to the third power, sine of x to the third power. Here's a trick. Whenever you see a trig function with a high variable and then another trig function after that, most likely the chain rule just occurred. Okay? What's going to happen is that, so tell me please, what is the derivative of this? What is the derivative of sine to the third x power, or to the third sine of x to the third power?
3 sine squared.
Sine squared. Why times cosine?
Because I just used the chain rule.
Because you just used the chain rule. Because you realize I took the derivative of this guy, but don't forget sine of x in itself, you have to take the derivative of. So that'd be times cosine of x. So again, anytime you see a trig function with an exponent right next to another trig function, that should tell you that maybe a chain rule just occurred there. Okay? So
I understand that one. I still don't understand number 8 and number 7.
so that would be f number 8 and number 7. So let's
Do you
see.
get it? Wait, can I look at your paper again?
And then number 12, what'd you guys get?
number 12. A.
Oh, I thought
You guys got A?
I got A.
No,
for 12.
H.
What?
H.
12? Oh, did I do that wrong? Oh, sorry, no,
You're
sorry.
looking at the wrong one.
I was gonna say, I'm like, I didn't doubt you too. I was like, well, Aaron's usually pretty correct, so what? Let's go back and do this in my head. Okay, so 12 is H.
Is this e to the x over 2, and then the derivative of the x raised 2, so the derivative of x over 2, and then you use the quotient rules. Those are and then you would get e to the x over 2 times a half.
Wait. It's this times what?
It's the original e to whatever.
So I'll give you guys a few more minutes to work on this. This is just kind of getting in your brain about taking antiderivatives and kind of working together.
What is
Let me write the actual chain rule for you.
So knowing how we did number 11, what would be the answer for 14? Let's test it out. So you say it's negative cosine
So
cubed
that's the chain rule.
x. So if I took the derivative, it'd be negative 3 times cosine squared x, and then you have to take the chain rule times sine of x. Is that what we got? Yes.
Times negative sine of x.
Times, oh,
Because
yes.
the negatives have to cross out.
Yes, times negative sine of x, and then the negatives would cross out, give me positive 3 cosine squared x times sine of x. Very good. Okay, very, very good. Very. That's a negative sine of x. Okay, so very good.
Yeah. You leave those
So let's see, 14 should be, what is that? M. If you're having trouble with number 15, rewrite that. Anytime you have a, like, anything 1 over x squared, or you have square root of x, any roots, then you can simply rewrite it as this x times 1/2. Can you find the antiderivative for x to the 1/2? Oh, what'd you get?
Yes, because the 2 and the 1 have to
so-
multiply together to get 1, which is just. Does that make sense?
You got-
So you think about what the power of x would be.
Uh-huh.
And
Kyle,
so if you have 3
do you want
over 2, then if you subtract 1 from that, you get 1/2.
You get it?
So that's right.
Uh-huh.
And then since the 3 over 2 would go in front, and you don't want a coefficient, then you do 2 over 3, so then they all cross out.
That's correct. Yeah, that's absolutely right. So if you took the derivative of this, you know that this would come down, right?
Yeah, but like,
How?
I don't know how they got to that.
Would be 1 over 2. Okay, but you have to cancel that out. So
Yeah. But it's
to get x
Oh.
over 1. Okay, that works. Okay.
At the top of the page, why does it say
If you
band?
take the
Yeah, I was
derivative
thinking
of
just
this,
putting like
you bring
volumes
this
down.
towards here. So
What?
the
Band?
one there, and and
Oh.
subtract.
What? At the top of the page.
Oh, I don't know. That's weird. Yeah.
Like usually it says like date or class.
Yeah. Like a. See, I would say a band out loud, but I'm like, I don't know how relevant I am with music, so I'm not gonna do that. Yeah.
We won't judge.
No, I'm alright. Okay. I was gonna say, yeah, like Metallica, right? Yeah, and you guys were like, what? Wow, he's really old.
Listen to it.
And then they
You know of them. That's fine, as long as you know of them. You know, like my
I
references.
know that they're like heavy metal.
I think at some point I'm really scared if I mention some, people are gonna be like, I don't know what he's talking about. So he's
I
he's
think I get it. 'cause
quite-
I
Kind of
did
saw
the
you as
English
an Imagine Dragons
even though I knew that had it in.
Imagine Dragons, man. What'd you say about
I
Imagine?
kind of saw you as an Imagine Dragons person.
Oh, really? That's cool. I like that. Okay, that's D and
Why did you cross it out?
what? Cross what up?
All the stuff there.
Oh, I just didn't want to make you. Maybe that's counterintuitive. I thought that'd be more confusing to have more work on the side, like and trying to link it up. I just want you to focus on this, but okay, maybe that's not a good idea.
You should. You should get like a notebook
Mhm.
and then label your problem and then do it that way. If one of us, because we're at least me, I'm slower than them,
Mhm.
so I'm still at like 9, and I could have seen that work, when I got to it. But
Oh,
one
it
of
made
us
sense
got
of
to see
it?
'cause-
I apologize. Yeah, you're absolutely right. I should be doing that. Yes. Let us do that.
Now that we figure out number 9.
Okay, so I'll give you guys about 2 more minutes and we got to move on, okay? Because I have a key for this as well. I do have a key, so you can go back and try to work this out on your own before getting to the other stuff, right? Because you're going to, what's up?
Negative
I'm trying
sign.
to do this now. To the letter.
Oh.
Because I haven't told you why you're taking antiderivatives. I'm telling you to, but there's a reason why, yeah.
Would you tell us like the application in real life?
Well, I'm about to today, what the application is, yeah. What the application for this is mathematically, and
Because
then
I get derivatives. Like if you wanted to know, if you wanted to map out a rocket's motion, like I can understand that.
Yeah,
Well,
Lots
like
of
for,
people map
like
out
in
rockets.
physics at least, like if you want to go from say
Oh.
position to velocity or velocity to acceleration, you take the derivative.
I
So
just
for
used a rocket
antiderivatives
because
to
it's
go
cooler.
backwards.
And you would need to know that for a rocket.
well, you know how you took the derivative of position to get velocity, right?
Yeah.
What if you were like, oh, I was given the velocity, but I want to know its position now. What do you have to do?
I guess you have to find the antiderivative.
Yes,
I wouldn't want to do that.
Well, at least you have that skill that you didn't like getting. But you're like, well, I know it. I just didn't like how I got it, but I got it. Right? I know it. So that's all that matters. And not just that, too. I mean, what's up?
I'm talking to myself, but I was going to say that, I mean, isn't the like application of this kind of stuff kind of limited anyways, because computers pretty much do most of the stuff for you. Like in the actual workplace.
That's
you literally
true.
Take out a pencil and paper.
No, that's very true. But when you're running these programs, you're a person that understands where it's coming from. So the tool set's only there for the user to use, but the user better know what they're doing with those tools, right? So in order to understand their tools, they have to understand the inherent math that goes in it. They just understand that the tool is there to save time, right? It's like I guess it's analogous to a person given a hammer, right? And they know what's it used for, and like what the alternative could have been is bashing in a nail, right? But if you give it to a person that has no application, has no idea what to do, they're just given a tool, right? So that's kind of the same thing. You're given the software that can run these programs, but what use is it if you don't understand what it's used for at all, right? So that's what the math understanding is for.
The derivative of this.
Oh, the derivative.
Or no, not sine.
Cosine. The derivative of cosine is negative sine.
All right, guys. If you guys like, I will actually put up the solutions right now, just for a brief second. Okay, so here's the other answers that were done before. I'm going to post up this picture, a picture of these solutions. And then you can copy down any that you need now, because we're going to move on to the trapezoidal rule. So this is actually leading up to 6.4 in integrals, but we're going to actually jump around and go to 6.5 now, okay? So bear with me, because there's a sort of a logical order with how the information is going to be given today, if I can get through it, okay? Okay. So let's take some more notes. Some more notes. Right? You guys can believe it or not. There's more notes. But Mr. Wade, this is my time off. I'm like, I know, but you're in the class, and we're in a class. We're going to take notes like a class. Okay. 6.5 trapezoidal rule. You're going to wonder why I'm going back and forth, but hopefully it'll be logical, the information, the way this comes out. Okay, so in the past, you are known to have taken the area under a curve, right? Does anybody know how does anybody remember back to how you would do that? So let's say I have x squared, okay? And I wanted to find the area under the curve from, let's see, from 1 to 2, okay? In 4, equally spaced parts, or equally spaced or equal width segments, or subintervals. And then your book would refer that to like n is equal to 4. That's how they would write it, okay? Then you would be asked to find that area, all right? So I'll just draw you the solution, or not the solution, but I would draw you what it should look like, okay? Here's where it is. So it's from 1 to 2, right? And then you would have to break 4 different parts equally between 1 and 2. What is that technique called when you do that? When you break this in, it's called a Riemann sum. So let's see. That's one segment, second segment, third segment, and there's a fourth segment right here. Say 1, 2, 3, 4. Does everybody see that? And let's see, you do, so the formula for finding that, these segments here, would be, it would be, you take the range, the bigger number, 2, and you subtract 1, and then you divide it by, let's say, the number of intervals you want, which is 4, so that'd be 1/4. That tells me that each of these things is 1/4 wide. So you can add that as like this guy over here, this interval over here should be 1 1/4, or this x coordinate should be 1 1/4. This x coordinate could be 1 2/4, and this x coordinate could be 1 3/4. Does that sort of make sense? Okay.
So like 1.5, you mean?
Huh? Yeah. So this would be 1/2. Okay. Well, this could be 5/4 if you want. Okay. Why not? Okay. Yeah, Skylar.
So how do you determine like is the number of segments just based on clarity? Like
They'll clarify for you. Can you do that for me? What is it? Space this out into 4 equally spaced segments.
Oh no, but I mean like how do you determine, like, is it a matter of efficiency as far as the measurement of how many segments there are? Because you could have like 5 segments or 3 segments. Like,
Just
the problem
tells you how
responds for-
many.
In this context, they'll ask you specifically to demonstrate that you know how to do it with 4 subintervals.
oh, okay, so it's just like
It'll be
a matter of
specified.
question. Okay, so
Like, I might
but,
specify-
Like, it doesn't really matter. Like it could be any.
It doesn't, but can you imagine though if you did 4 equally spaced segments? That this is the original method that we did it with. We did it with rectangles. So here's what it would look like. There's a rectangle limited there. There's a rectangle limited there. And there's a rectangle limited there. And you'd have to take the area of these rectangles, right? What's the problem with taking the area of each of these rectangles?
Because there's a little triangle, but that's not.
So is that an overestimation or an underestimation of the actual area from 1 to 2 underneath the curve?
Underestimation.
That's an underestimation. What do you think would happen if I had more subintervals? If I had more rectangles? Sorry, this is a little bit of review, guys. So that's a Riemann sum, okay, by the way. So in case you missed being there. But let's say from 1 to 2 again, right?
The 2 minus 1 over 4,
What's that?
that part.
Yes, the 2 minus 1 over 4. And then you see how wide these intervals are? They're 1/4 wide, right? Well, how many more intervals would you like to add to that?
Just start off with like add one rectangle, kind of just
Give me a much higher number, but give me a slightly higher number.
Just do double.
4.
Yeah, 4 more. Then we'll do 8. So we'll do a. Let's see. That's 1, 2, 3, 4, 5, 6, 7, and then 8. Okay. So watch these squares here, or these rectangles.
You can't see.
Oh, sorry about that. I was in my own la la land there, right? Okay. Do you see that there's still an underestimation, Skylar?
Mm-hmm.
But would you say those triangles are as big as the triangles that we ended up having up here? So what would you say about if you had to make a comment, what would you notice about adding more subintervals?
So it's less. It's still an understatement, but it's less of an understatement, kind of. So more.
Well, how accurate? How much more?
Precision.
Yeah, more
Precision was the word I was looking for. I'm like, what is that word?
more precise or more accurate. Okay, this is more accurate. The more squares you can fit in, or the more rectangles you can fit in, the more accurate the area under the curve will be. Right.
Okay.
However, is this, would you say, the best shape rectangles in this instant? It's fine, fair enough. Okay. Okay. All right. Let's see. Give me 1 second. I don't know why that happened.
It's Chopin. That's right.
Chopin, right? Oh dear. Okay. But think about that for a second. In that curve, right? Oh, I think I understand why. Because it touched that button. Okay. No biggie. Hopefully everything works out. It's a shame, but I guess this means we're gonna have to do this to. We're gonna have to transfer this over to the board.
there it is.
Oh. Okay, so let's look over here though. Could you think of a shape that is better underneath this curve? Now, it's the same idea. Intervals are the same, right? But is there a better shape we could fit underneath this curve to estimate the area in place of the rectangles instead? What do you think would be a better
A trapezoid.
trapezoid?
Well,
So
I'm guessing is that like the trapezoidal theorem? Is that why it's named?
good
I would have said
guess.
circles for stars.
Well, or hold on, let's explore circle. Why not? Let's explore circle from 1 to 2. What are you laughing at, Benjamin? Okay. So 4 equally spaced.
I would
1,
not
2,
do
3,
circle.
4.
Okay, when I was thinking that though, I forgot they have to be evenly. I forgot that they have to be evenly spaced because my circles
think
would be
your
like tiny
circles are
circles and then
ovals.
bigger circles.
But hey, it's good
I
to.
can see.
Why not circles? Okay, like.
Those are not circles.
Okay, fine. Those are ovals. Whatever you guys want. Okay.
I think it's just as bad as the rectangle. It's not that bad.
It's not that bad, right? Ovals. They're pretty good,
I
but
think it gets worse though as you go up. Honestly.
okay. But
Yeah.
there is a reason why this is called a trapezoidal. What is it? Trapezoidal theorem. Because the trapezoids might be a little bit more accurate. So here's what the idea should look like. So 4 equally spaced parts. 1, 2, 3, 4. We still determine the width by the same method. Okay. It would be 2 minus 1, the range, over 4, and that would still give us a width of 4. So the spaces are the same, but now the shape should look like this. We try to fit it. We try to be right there. Try to be as accurate as we can. Let's see here. It's not going to fit exactly on the curve, but let's see here. So that's sort of the idea. Does everybody see that now? I know it's not perfect, but
The angle has to be the same on each one, right?
Yeah, probably.
I believe so, yes. But does everybody see the trapezoids that we're trying to make at this point? Yeah? Okay, I didn't draw them perfectly, but you understand that trapezoids might be a little bit more accurate. There's still slivers that are an underestimate, but they're still good, right? So let's explore trapezoids with a little bit of review. What is the area for a trapezoid? Take a few seconds to discuss with the neighbor.
B is over 2.
BH2.
Yeah, that's a triangle.
So let's look at a trapezoid here, if you remember.
Oh, they have 2 different bases. They have 2 different bases.
Yeah, well, we did
I
that.
would just add the area of the 2 triangles.
Oh, you
To
could
big thing.
you could do that too.
Honestly, I don't actually.
It's all right.
I'm pretty sure there's like one.
So the area for a trapezoid, you can write this in your notes. The area of a trapezoid, so to make sense of this, the area of a trapezoid is 1/2 times both bases, base 1 plus base 2, times the height. Okay?
That was close.
That was very close. That was very, very good. And remember, I'm sorry, so just to kind of go back, we were looking at this curve. This curve is the curve of f of x is equal to x squared, right? F of x is equal to x squared, okay? F of x is equal to x squared. So you know what? I think I actually grabbed this from a page in your book, 315. All right. Okay, everybody got the area of a trapezoid down? Are they trying to replicate the perfection and the beauty of my drawing up here?
My drawing's better.
What?
Sorry.
Those are fighting words, but it's okay. It's okay. Okay, so there it is again. I know it's kind of hard to see.
Did you draw your book?
It looks like someone drew this before my time, right?
Are you sure?
Yeah, that's odd. Okay. Huh. How odd is that? Okay. So let's take a look at this. It's the same thing. This is the same exact thing, okay? But simplify another way from how other people might simplify it. It's not just 1/2, right? But this is 6/4. This is 5/4, right? They're all equally spaced. They're all about 1/4, 1/4 width, right? What would be the area for this trapezoid, this first trapezoid? What would be the area for that first trapezoid? So I know that you might not see it, but the height is 1 for this length, and this length is 25/16. But just based on what we have here, what is the area for that first trapezoid? Using this formula that we know.
Does the answer have to be in fractions, or can I just plug this into my calculator?
You can plug this into your calculator, or you could just tell me how you would set this up. How about you just tell me how you would set that up?
Put the lengths of the bases in.
Okay, the length of the bases, and what are the
So
bases
1
though?
plus 25/16, and then the height would just be 1/4.
Yeah, nice. Because the trapezoids, like this is the height, and these are the 2 bases, right? And remember, we're finding the area for that. We just found the area for that trapezoid. But remember, I want to find the area under the whole curve. So can we do that for each trapezoid? Each of the next trapezoids?
It looks like besides the one that you drew on,
Uh-huh.
like that it's covering the whole curve. Like it's because how you drew it, there was like a little sliver that wasn't.
Oh, that wasn't actually there. Yeah. I wanted to exemplify that. Yeah, like it happens to be that the top diagonal actually does fit along very well with the curve here, but you should recognize that when you do the trapezoids, there's a slight space between the actual curve and the actual diagonal of your trapezoids that you're drawing. So every trapezoid that you're drawing, you might not see it because it fits so well along this curve, okay? It happens to have.
Because it has to be straight.
It has to be straight.
And this is a little slightly curved, but
Yeah.
you can't really tell that much.
That's right, because the function is x squared. We know x squared gives us a parabola, which just gives us a curve. So if you try to match straight lined trapezoids that diagonalize like this, okay, to a curve, it's going to always be a little bit off. The straight line might go over the curve, it might be under the curve, okay? So, well, I think most likely it'll go over.
Is it okay for there to be different angles in each trapezoid? Because, like, it gets more straight.
Yeah, it's fine because like we said, this is just an estimation, right? It's not going to be a perfect area. We learned that from the Riemann sums, that it's just an estimation, right? And we also learned from earlier discussion with Skylar that the more intervals you put, the more trapezoids you fit in there, the more accurate your area will be. One step after this, though, is learning a way to get it 100% on the money right. Okay? Yes?
Would it possible for a curve, like, for a curve's area to be like a whole number? Like, or is it always going to be like a decimal? Like,
It just depends on what your quote-unquote curve is.
yeah,
Because what if you were doing the area under a linear function?
that's right.
You-
So
You mean like the square?
Like a square, or yeah, a square, or if you had just like mx plus b, right? A straight line, you have a higher likelihood of making an area that is a whole number, right?
yeah, I was going to say like what kind of math would it take for like to have a curve, the area under it be a whole number?
Well, actually, that's the application here isn't necessarily to do that, to try to get a whole number. It's just so like I would suggest watching the video. Like we couldn't record, I couldn't get a good recording of our last lecture. But if you took the area under a curve, it'll tell you a bit of information. Like it depends on like what your y-axis is. Maybe your y-axis is in meters over seconds, which is a rate, and then on the x-axis, it's time in seconds. If you found the area under that curve, think about it. The area under the curve would be meters over seconds times seconds. What's the unit that you would end up with?
Acceleration, correct?
Or no, it's meters over seconds, m over s times s.
Oh, right. I mean,
It would be,
but would that be acceleration or minus?
you would be finding m times s over s.
I did that wrong.
It's okay. You'd be finding the distance. It's telling you information. You're using this technique to find information. So sorry about this, guys. I'm going off a tangent a little bit here.
Sorry, it would just be interesting. Like, what kind of curve would it take to like get a whole number? Like, that would just be interesting.
If you wanted a round number, wouldn't you just set up an equation and put it equal to whatever number you want to find? If it was that important to you.
Yeah, if it's that important, yes. Or it depends on your range too, because you see how we're going from 1 to 2.
Mm-hmm.
Imagine this being a line like that, right?
Mm-hmm.
And for here, if I cut off my range from 1 to 2, then maybe that'll still give me an area with a decimal. But it just depends. If you want to have an area with a whole number, maybe it'd be better to start from 0 to 2.
Right.
It's up to you.
Like reverse engineer it, kind of.
Reverse engineer it, yeah. So it all depends on your parameters,
Okay.
but the main thing is, it's just that's not what we're trying to do here.
Okay,
We're just finding area under a curve given whatever. From 1 to 2, underneath this curve, what's the area? That's all you need to know.
Okay.
Okay, so that's all. That's what we got for the first trapezoid. How about the second trapezoid? Someone give me the area, or how to set up finding the area for the next trapezoid.
The same way as we did the first one.
Okay.
Except it'd be inside the parentheses, it'd be 25 over 16 plus 36 over 16.
And then again, we still have to consider the height, which is again 1/4. So that's the area for the second trapezoid, right? So we're adding the area of this trapezoid to the area of this trapezoid. So again, this is 25 over 16. This is 36 over 16. How about the next trapezoid? This third trapezoid in here. It'd be plus 1/2. Because remember, the area of the trapezoid is 1/2 times base 1 plus base 2. So that would be, 36 over 50, or what is it? 36 over
16.
Plus
7 over 8.
7 over 8? Oh, you're trying
never
to,
mind.
are you trying to simplify that? Is that way? Okay. It would be 49 over 16. Okay. And then the area of the last trapezoid. Oh, sorry.
Make sure you do 1/4.
Plus the area of the last trap. Yep.
You can make it 1/8 just to combine.
Okay. All right. I see your shortcuts right now. So it's going to be 1 over 2 times. Sorry. I'm going to write this out first. Then we're going to explore the shortcuts. Okay.
Shortcuts.
Okay. So does everybody see that? 4 distinct trapezoids, right? These are areas of 4 different trapezoids, right? Okay, so can we shorten this down a little bit? Okay, so we notice that all of these heights, right? All of these heights are, what is it, a quarter, right? And each of these terms has a half out there, right? So, okay, so if I had to rewrite it again, you don't have to rewrite this. I'm going to do that. That's like the first step. The second step would be to realize that all of them are being multiplied by 1/8, right? 1/2 times 1/4, 1/2 times 1/4 is 1/8, right? That'd be 1 plus 25 over 16 plus 1/8 over times 25 over 16 plus 36 over 16, right? Plus 1/8 over 36 over 16 plus 49 over 16, okay? Plus, you guys are already getting tired of this, I can see, okay? 1/8 over 49 over 16 plus 4, right? That'd be the second step. Could we simplify this even more? Okay, how would we simplify this more?
Just take out the 1/8.
Take out the 1/8,
And then add them all.
then add them all. 1 plus 25 over 16 plus, there's another 25 over 16 plus 36 over 16 plus 36 over 16 plus, what?
You should have probably written 16 over 16 instead of 1.
Oh.
So you didn't have to extra step.
I see what you're saying. Okay. But you'll see there's a bigger idea here that I'm trying to get to right now. Right? Can we simplify this even more? Now, this next way I'm going to simplify it is going to seem a little odd the way I chose to simplify it. But it's to prove a point, okay? Or it's not just to prove a point, but it's going to be to prove something that you're going to see in your chapter, okay? It's going to be 1 over 8 times 1 plus 2 times 25 over 16 plus 2 times 36 over 16 plus 49 over 16. 2 times 49 over 16.
Used a colored pencil.
Huh?
Things like that.
It's just funny when you just have to fit the light out.
Oh. Well, I just want to be as perfect as I can be for this. Okay. Now, if we take a look at that, and you know what? Why don't we go back and separate out? Remember how this was 1/2 times 1 over 4? Let's keep it that way, right?
So then get rid of it too.
Or actually, let's just. Why don't we just? I think. Let me find a.
You could just leave it.
So let's see. The trapezoidal rule. Okay.
It seems like a lot of work if we were doing a problem like this.
Okay.
Like it would take so long.
So what do you say? It's.
Problem.
Why don't we make this into a general formula?
Oh, so this is the proof.
This is, you just proved this, that you took 1/2. It's always 1/2 times, what was 1/4? What did 1/4 represent?
The height.
The heights of the trapezoid, right? Times the height. And then let's actually call these different heights. This is y1, this is y2, y3, y4, and y5.
Different bases.
Different bases, right? I know those are, it's weird, but yeah, they're bases, right? But let's just call them, just go back to being y's because they're heights, right? Or what?
Under the XY
You
coordinate
understand?
system.
Under an XY coordinate. Go ahead. Under the XY coordinate.
It just makes more sense.
It just
What
makes-
you were saying.
Okay. Yes. It makes more sense if we just understand this as X and Y of the XY coordinate, right? So let's say that that's Y1 plus, what is it? 2 times Y2, right? That's the second height, plus 2 times Y3, plus 2 times Y4, plus Y5, your very last height. The truth is, it doesn't really matter what the number is. We just know that we notice that all the heights in between the first and the last height are always multiplied to 2, right? Yeah?
Is h the change of x?
Yes, the change of x or the width, basically. Yeah.
Because I feel like, if you wanted to put y, you should be more consistent.
You put
and
X.
and y, or h.
Well,
and
there's a reason why I'm writing to you like this. Yes, Skylar?
Could like at the Y5 at the end, could it be just YN? Like,
Because
because it could like
it can go on and on forever, but we
Yeah.
we noticed that what if this kept going on forever? Okay? Meaning this. It's 1/2 times like I didn't just stop at 2. I was like, let's go to 1,000,000. Why not? Okay? Okay? It would still, when you say it would still be the first height plus 2 times y2 plus ... doesn't matter. But eventually we get to the very last guy, and it's yn, right? Let's just say it's the very last height, right? We took the very, like, what if I kept going on and on forever? It kept going line, right? What I just proved to you is you can do this for any trapezoid or any set of trapezoid underneath a curve. And then what you're going to see is in your book, they have this, what's called a general formula. Okay? It's basically saying the same thing. It's 1/2 times the height, which is h over 2. And then what they call it a little bit different, but they said it's the first height plus 2 times the second height to blah, 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 blah. And this is still nothing different. It's just saying to like the second to last height, 2 times the second to last height, and the very last height, you don't need to multiply it times 2, right? You can plug this in for any problem, and then you should solve the area under the curve, okay? That's the formula for the trapezoidal rule for solving the area under any curve. With any set of trapezoids. Okay, so I know that didn't come out very well, but let me see if I can see if I have another problem. Just a sample problem that we can just do. Let's see it's 2:52 already. Okay, so looks like we're gonna have to get to integrals next week. So it's good that we had this class, or else we would have never done with this stuff. Okay. So I did all that work, right, for this. And then right next to this should have been the general formula trapezoidal rule for the trapezoidal rule. For the trapezoidal rule. This is the general formula for the trapezoidal rule, okay? Let's just go back, okay? Let's just go back a second. So you're like, what the heck just happened here, okay?
Wait, why are we going back?
No, because we gotta realize what the heck I asked you. Like, what was the question in the first place, Mr. Wade? I have no idea what the question was anymore, okay? So let's just...
The area under the curve for 4 segments.
Yes! Okay,
I
so...
wrote it down.
Okay, so if we had to go back. Original question. The original question was... Okay, and then let's just make this a little bit more specific. If your f of x curve, or f of x was x squared, what was the area under the curve from 1 to 2
Inches.
in 4 equally
Oh, I thought it was inches.
spaced, let's say trapezoids. N is equal to 4, okay? What you would do now is to rewrite delta x, or just say the height is equal to 2 minus 1 over 4. That was 1/4, okay? The only thing that they really didn't make it very clear, I didn't make it very clear, but you have to kind of use the diagram. We can just say that we'll just list out all the heights, okay? y1 is 1, y2 was 25 over 16, y3 is equal to 49 over 16, and then y4 is equal to 4, right? Those were all the heights, let's say, okay? Now, if I asked you for the area, how would you plug this into that formula that we just created? So going back to this formula here, how would you plug all these numbers into that formula? How would you do it? Yep. Okay, so you just put them in. Okay, Mr. Wade, just put them in. It's that simple. Okay, so here's the general formula. It was like 1/2 times h plus in parentheses y1 plus 2 times y2 times 2 times y3 plus, and then the very last height is y to the y fourth. Okay, so that means the very last height we don't multiply to 2. Okay. Whoops, forgot I'm using this one. So it'd be 1/2 times, what's the height? Then 1/4. And then let me separate these out into different bullet points. This was step 1. This was step 2 to list the heights, and step 3 was this one here. Be like 1, okay, the times 2 times what?
5 over 16.
Oh, you got it. Times 2 times
49 over 16.
then
Times
or plus
4.
plus 4, yeah.
Plus.
And then you would add all that together.
So you just, if you already have the equation, then you skip a bunch of steps.
If you were given the heights. What do you mean? Yeah. If you have the equation.
Before you had to do like so many steps.
If I had to do this by hand from my own imagination, I would go through this many steps.
You'd be a smart cookie.
Yeah, well, the guy that originally created the person that originally created the formula was a smart cookie. I just followed this thing. Huh?
Smart pastry.
Pea string. What? Pea string. All right. Very smart pea string.
Include all desserts.
Okay, all the desserts, okay? So for us, what we're going to do is we're just going to use the general formula. But you know where it came from now, right? Do you want to prove that over and over again, where it came from?
I actually like proofs. They make it make sense. Like I
does,
I
right?
appreciate the videos you put on the product and quote. Actually, I didn't like the quotient rule video because he didn't explain it. He was like, "This is a lot of technical junk." I wanted him to.
I didn't know that.
Yeah.
I just posted up there, so I'm sorry.
Yeah.
Okay. Will you trust me if I just gave you the answer for this for now? Or yes, please. I don't know. No more mystery. Okay, I'm good. Okay. You would put this in your calculator and just be 2, 3 repeating. Okay. You don't even have to write that. You can just write or 2.3 repeating. Okay, that'd be enough. Nice. You did it by the hand. Okay. And does anybody know the fraction, the mixed number with a fraction? What that would be? It's not just 2.3, right?
7 over 3.
It would actually be
7/3.
7/3. Oh, yeah. It would be 7/3 or 2 1/3. Okay. Benjamin's got a low smooth. Yeah. Okay. Now the antiderivatives and the relationship to all this stuff we're not going to really get to talk about today, but that's good. This tells me that I didn't even have time to go through this in one day. So hopefully the other students will watch this video. But hold on. There's one more concept to go through. So that's the trapezoidal rule, okay? That's the basis for understanding the trapezoidal rule. Now, this is going all the way back to, this is going to be an introduction to 6.4. You've already sort of had an introduction with 6.4, which is integrals, okay? But let's say that we took this here, right? And I'm going to write different notation for this. So from our previous problem, you solved, this is what you solved for. Are you ready for this? This from here.
So
I'm going to ask you what this means. This is what you solved. But
yeah.
okay, so
That's what I did.
look what we just did. Hold on. To summarize this, okay, if you need to go home, go ahead, go. Okay? So this is what we just did here. But what the heck does any of this mean?
The antiderivative.
Oh, you're jumping ahead, young lady. Okay? Don't make those relations yet. Just tell me what you solved for. What did you just solve for? Don't even look at this. What did you just solve for? What does 2.3 even represent?
The area.
Curve under the given.
Under the curve of what?
The given interval of the.
X squared.
X squared. So more specifically, this should say x squared. And dx is just what you don't understand is that means with respect to the variable. What was the variable that we used? It's x. Okay. Just to answer your question. Okay. Because that's the variable. Okay. Just
Would this be right? Oh, wait,
Yes. Oh, yes. Hey, you're not supposed to get there. No.
Okay.
Go back. Okay, hold on. So let's dissect this. Yes, go ahead.
Is there a name for this notation?
Huh?
Is there a name for this notation?
Yes.
Integral.
I'm glad you asked, good sir. Okay, on. You're gonna put page 284 in your book. Now, don't be mad at me. I'm sorry, but I just think I'm teaching this in a way that's a little bit not more logical, but it will make more sense explaining it for me at least. But I think it's a lot. Okay, so this is from 6.2. I just think the information they present to you is a little bit out of here. Okay, this is what all this means. But they have all these different names for the different parts of what we just wrote down. But I want to talk about it. Right? You found that it was the area under the curve, right? We found the area under the curve from 1 to 2 under the curve of x squared, right?
Mm-hmm.
With respect to the variable x. And then we found it was 2.3, right? There's another name for this area under the curve. I'm going to put that in quotes, okay? That is the integral.
Yes. I knew it.
You took the integral from, quote unquote, from 1 to 2. Okay, sorry about that. Another name for this, the more legitimate name, are the limits of your integral. Like the upper and lower limits. That's the lower and that's the upper limit. Okay? That's it. So, hold on. So, if you want to know each piece, though, what it means, okay? This is technically called the integrand. So, sorry. Here. So, that's what we got in our notes, right? If you want to be more specific, okay, page 284 is more detailed notes in parentheses. I'll make a note to myself that in page 284 on your book, okay, technically it's the integral, but that's an integral sign. A to B is the upper and lower limits, right? F of x is the curve, otherwise known as the integrand. This would have been a hard way of learning it, right? I think it would have been a little bit tough to dissect what this means, but we were perfectly fine in understanding it without having to look at that, right? But if you had to be technical, each of these components does have a formal name, okay? Did you like having to calculate that area that way? The trapezoids? You guys don't like the trapezoid rules? There's a much easier way that unfortunately we don't have time to go through today.
It's so funny. You're like, there's this way, and there's this way, and there's this way. They're all the same thing.
Well, it's not just that I'm saying like, guys, check out this way, check out this way, check out this way. It is interesting to me, but if I had one way to do it, it'd be the one I'm about to show you next week when you come back.
You always leave us at a cliffhanger every single class.
Okay, well, I'm glad you interpret it as a cliffhanger, or just it could have been like, I don't want to go to the next class. But in your words, it's a cliffhanger. So that means it's entertaining to you. So you're excited about it. Okay? So the reason why I'm teaching you all these different ways is these are the standards we have to hit in the AP Calc course. Okay? So I'm not just doing this to show you and just be like, do you guys like it? No. Okay?
Are they like proofs for the way you're going to teach us Wednesday?
No. The way you're going to do it has to do with what you did in the beginning of class.
The antiderivative.
The antiderivative.
The one that I did.
The one that you did. Yes. Okay. The one that I think everyone was working on. Yes. Okay. So we will continue on with the last method, 6.4. Okay. 6.4 is what we're going to start on this next class. Integrals. Now we're going to learn about integrals. Okay. I wish they would have taught you 6.5 as 6.4, and this would have been the last section. Because it all comes to a head right here. This is the easiest way to figure out these areas under the curve, okay? And by the way, these 2.3, since it wasn't perfect, sorry, I'm going to say our integral was about 2.3. Because the way, huh?
It was perfect.
With the trapezoids? Well, the trapezoids
yes, but okay.
Well,
2 1/3 was perfect.
2 1/3 was perfect.
He's talking about because there's a smidgen of space.
Yes. When we get to Monday, this will no longer say is about equal to 2. It's going to be on the money, okay?
I have a question really quickly.
All right, I'm gonna stop. Hold on. Yeah. Go ahead. What's your question?
So Monday, would that be like calculating the error of this?
No.
Or is it totally different? Okay.
Monday's gonna be a totally different method that there's no error.
Could you calculate the error of this? Like, what if you had that kind of a problem and you wanted to know if there was any like percentage of? Why are you giving me that?
There is, but that'd be like trying to find the areas of the triangles underneath the curves and stuff.
Okay, that would actually be fun though, because in chemistry we would have to do that.
The error? You
Yeah,
like
we have to do
calculating for
stuff like
error?
that in chemistry.
You are literally the only person I've ever heard. Why don't we calculate the error for fun?
I don't like doing it.
I love it though, Deja. That might indicate to me that maybe you are a fit person to explore math in college because you are just that inquisitive about it. Okay? That should tell you a lot about yourself and your interest in math, right? Even though you say, I dread it, but let's just do this for fun anyway. Okay? Okay. That doesn't really coalesce, but all right. Whatever you say, Deja. Okay? All right, guys. Let's reconvene Wednesday to finish off
Wait,
these
did
chapters.
you guys do anything with this?
No. That's just another antiderivative worksheet
Okay.
to work on. So.
You want to post a key for that worksheet on the
Yep,
website?
keys to both of these worksheets if you like. Okay, so
Great.
let's go ahead and stop.